Okay, so now let's look at the solution for example 1.1, where we're looking at the amount of electric energy that was generated throughout the year and the amount of money that was saved throughout the year when using a wind turbine to produce electricity. Okay, so first we're going to start off with our knowns, right? So here we have our knowns, 9 cents per kilowatt hour. We have a certain amount of power that's being generated, so you'll see there's an E dot. So the E stands for the energy generated. The dot means it's an energy rate, right? So an energy rate is the same as units of power. In this case, we're at 30 kilowatts, which is 30,000 watts. Each watt is equal to a joule per second. So the dot just means you take the unit and divide it by seconds, right? So in this case, energy, which would be joule, or in this case, kilojoules, and the dot creates a time rate, right? So now instead of joules, we have, or let's say instead of kilojoules, we have kilojoules per second, right? So the energy rate is 30 kilowatts, or 30 kilojoules per second. That's also known as power, right? So a unit of watt or kilowatt is for units of power. And the time is 2,200 hours. So there's 2,200 hours over 365 days, which gives us about 6 hours per day, in which case the wind turbine is, fully operational, let's say. So we're asked to find the electric power generated per year and the money that is saved over the course of the year. Right? So if we look at the energy generated over the course of the year, we can take the energy generation rate, right? That's the kilojoules per second, and we can multiply that by time. Instead of sticking with the kilojoules per second, let's just do, this is sort of a quick way to do a calculation for energy when we're given power. And so we have energy over the course of the year is equal to 30 kilowatts. If we multiply that by a unit of time, so 2,200 hours, we're left with 66,000 kilowatt hours. Now we can actually convert that value into kilojoules if we like. The problem didn't tell us to do that, but we could do that. So we could say that there is a kilowatt is equal to a kilojoule per second. So there's 30 kilojoules per 1 second. 60 seconds in 1 minute, so the seconds now cancel. We have 60 minutes in 1 hour, right? So the minutes will cancel there. And we can multiply that by the 2,200 hours that the turbine is producing electricity each year, right? So the hours will cancel there, and we're left with units of kilojoules. So you notice here that the energy is 2.376 times 10 to the 8th kilojoules. Okay. And if we want to calculate the money saved, we can take the energy throughout the year, multiply that by the unit cost. In this case, we were given information about the energy value in terms of kilowatt hours, right? So 9 cents per kilowatt hour. We determined earlier that we had 66,000 kilowatt hours of electricity production per year. So that gives us 66,000 kilowatt hours times 0.09. You can see the kilowatt hours cancels out. We're left with dollar value of $5,940. Here's a couple quick notes here. 30 kilowatt system installed is about $3,300 per kilowatt to install. So about $100,000 for a 30 kilowatt system. And you'll notice that the ROI, which stands for return on investment, the ROI is $100,000 divided by $5,940 in savings per year. So it takes about almost 17 years for that wind turbine to pay its way back, right? To pay for itself. Oh, excuse me. For what it's worth, the life expectancy of a wind turbine is up to about 30 years. And remember, this number is highly dependent upon the number of hours that the wind turbine is fully operational. So if you have a more windy area, that value would go down because you'd produce more electricity and therefore have more savings in your electrical bill each year. And then obviously areas that have less wind, it would take longer to pay off. Okay, so that's example 1.1. Let's go back to the lecture slides and continue with our lecture notes here. Okay, so the next, one of the first intensive properties that I want to talk about, because we use it very frequently in our class, is called specific volume. So a lot of times we're going to be using this term specific in front of things, right? So specific volume, we're going to have something called specific internal energy, specific enthalpy, and specific entropy. Anytime we see specific, all it is we're taking the term, whatever the property is, I guess is what I should say, we're taking the property and we're dividing it by mass, right? So in this case, specific volume, we're taking volume, and the minute we make it specific, we're dividing it by mass. So if you remember from a couple slides back, volume is actually an extensive property, right? And so what we're doing by making it specific, by dividing it by mass, we actually make it an intensive property. So you'll see here, specific volume is the volume occupied by a unit of mass of a material. So we're taking the amount of volume and the amount of mass that is contained within that volume. It's the reciprocal of density. If you remember probably back from chemistry, you may have even, you used it in statics as well. Density is equal to kilograms per meter cubed. And so it's the reciprocal of density. It's 1 over density. It's an intensive property now, right? And as I mentioned earlier, volume and mass are both extensive properties, but when we take the ratio of the two, we actually end up with an intensive property. So specific volume is denoted as a lowercase italicized v. So it's v is equal to 1 over rho, right? So specific volume is equal to 1 over density. So it's meters cubed per kilogram. And so if I were to look at the specific volume on a molar basis, that's with the bar on top, then it would be the molecular weight times the specific volume. And so the molecular weight is in kilograms per kilomole, right? So if I take meters cubed divided by kilogram, and I multiply it by kilograms per kilomole, the kilograms end up canceling out, and I am left with meters cubed per kilomole, right, instead of meters cubed per kilogram. For what it's worth, in this class, we don't use the molar basis for specific volume too frequently. It's used a little bit later on when we talk about the ideal gas law. We use it a little bit then. But in general, we almost exclusively stick with the specific volume and don't really deal with the molar basis too much. Okay, so another important intensive property that we'll be talking about throughout the semester is pressure. It's the normal force exerted by a fluid per unit area, and as I mentioned a moment ago, it's an intensive property. There's a couple different kinds of pressure here. One of the I guess most important kinds is absolute pressure. So it's the pressure with respect to a complete vacuum. So absolute pressure meaning that we are comparing the pressure to a pressure of absolute zero, right? So you can imagine anytime that we're comparing the pressure to when pressure equals zero, that is absolute pressure. So you can imagine a vacuum would be something like outer space, and a lot of times you can think of it as just the actual pressure. Since we're on Earth, we have an atmospheric pressure that affects all of us at all times, right? It's always around us. So on Earth, it's convenient for us to use what's called gauge pressure. So this is the difference between the absolute pressure and the atmospheric pressure. So gauge pressure is equal to the absolute pressure minus the atmospheric pressure. Essentially what the gauge pressure does is it tells us the difference between the atmospheric pressure and the pressure of, it could be a tank of gas or whatever we're measuring, right? So it does not account for the atmospheric pressure. All we are saying is the difference in pressure between what we're measuring and the atmospheric pressure. Here's a good example of how pressure varies on Earth, right? So you can imagine if you're at sea level or close to it, let's say 1,000 feet, and you walk up a mountain, right? Let's say you walk up a 14,000 foot mountain. You go to the very top and you finish drinking your water, and you have an empty container of water, right? So you go up there and you open your bottle, you close it back up. Now this bottle is filled with the air pressure that is contained at 14,000 feet. Now you can imagine that as so you can think of the atmospheric pressure that's sitting on all of us, that's acting on all of us, is dependent upon how many air molecules are sitting on our shoulders, right? So the closer we are to sea level, the more and more air is sitting on our shoulders, whereas the higher in the sky we go, the higher the altitude, the less amount of air is sitting on our shoulders, right? And so basically what this is trying to show here is that the pressure in this container is lower at a higher altitude. Essentially, there's less molecules sitting on top of this hiker's shoulders, or you could think of it as less molecules acting on the outside of this bottle. And as you go down, so if we keep it closed, remember the pressure inside the bottle is equal to the pressure on the outside of the bottle. And as we go down to lower altitudes, the pressure on the outside increases, right? More and more air molecules are piling up on top of the bottle and on top of the person hiking, that kind of thing. And so what happens is you can see that the bottle collapses because the outside pressure increases in comparison to the inside pressure, which was the same pressure at 14,000 feet. So pressure does vary depending on your altitude, and there's other things. For instance, if a storm is coming, you might have an area of low pressure or something like that. But in this class, we won't deal with pressure variations. We just assume that the atmospheric pressure is 14.7 psi, or 101,325 Pascal. Okay, so let's look at some pressure measurement. Here we have a manometer. It uses an elevation of a liquid to calculate the pressure, right? So in this case, we have let's say we have a tank that's filled with some sort of a gas, and it's pressurized, pressurized gas. Those molecules have a certain amount of force, right? So a certain amount of force on a, let's say cross-sectional area. In this case, if it's a circular pipe, it would be a force on a circular cross-section. Well, that force, in this case, is forcing a liquid to move up what we call a column, right? And so we end up with a height difference between, basically the height difference is the column height, right? And so that, based on that height difference, we can actually determine what the pressure is inside the tank. So in this case, the tank pressure is equal to, if we look at the absolute pressure calculation, remember that takes into account atmospheric pressure. So the absolute pressure calculation says it's the atmospheric pressure, right? We have a certain amount of atmospheric pressure acting on the fluid. In fact, it's acting on everything, on the outside of the tank, on the piping, or whatever, the tubing. It's acting on everything. But important to this important to the equation is that the atmospheric pressure is acting on the fluid, right? So we have the pressure of the tank. The absolute pressure of the tank is equal to the atmospheric pressure plus the density of this fluid, right? The density of the manometer fluid times the gravity, which obviously on Earth is 9.81 meters per second squared. If you were on a different planet, that value might change. But anyway, density times gravity times the change in height in this column, right? The height difference in this column. Now, if we were looking at the pressure of the tank in gauge pressure, remember that does not take into account atmospheric pressure, so it's almost like canceling this out. So we have gauge pressure is equal to density times gravity times height. And so the manometer is actually fairly commonly used in experimental setups and things like that. So here we have an example problem, example 1.2. Again, I suggest that you pull out a piece of paper, pull out a pencil, try and work through this problem on your own before looking at the solutions. The solutions are in the lecture notes, and you can go through and check your answer to see if you have the correct answer. So I'll just go ahead and we'll set up the problem. I'll briefly discuss what we're being asked to solve, and then I will stop the video, and that will give you some time to do your own calculations, and the next video we will talk about the solution. Okay, so here we have a manometer. It's used to measure the pressure in a tank. The manometer uses mercury as the manometer liquid, right? So in that case, the density is an important value that we need to know for this manometer liquid. So the density is 13,579 kilograms per meter cubed, and the column height is 55 centimeters. So what we mean by that is this H is 55 centimeters, right? If the atmospheric pressure is 101,325 Pascal, then we want to determine the absolute pressure in the tank. Now remember, absolute pressure takes into account, we have to take into account the atmospheric pressure in that case, okay? So go ahead and work through the problem, and the next video we'll talk about the solution.